We'll let Isaac join hopefully later. Steffi asked a question that may have been puzzling you. If you go into OWL and look at the homework, you'll see that the due dates on the homework and inside OWL are all at the end of the semester, whereas the due dates for OWL in the syllabus are coincide with the exam schedule. The reason I do that is that OWL has a nasty habit of shutting down your homework at the due date. So if you don't have your homework in by that date, then it'll shut down and it won't let you look at it later if you need to review. So I just made all the OWL due dates at the end of the semester, then you have access to it all the way to the end. And then the due dates in the syllabus, I don't actually have penalties for late assignments. So technically you could turn them in late if you want. That's not advisable because after the due date for the OWL homework, you're in a new material. So you're actually shooting yourself in the foot if you procrastinate. Okay, so today's going to be review for exam 1. And let me... For the benefit of the recording. Okay. So like I always do, even in the in-seat classes, I open it up for questions, specific problems that you have so that we get them covered before we run out of time. So I'll let you, the review documents are by chapter. So we've got one for chapter 10 and one for chapter 11. So what I'm going to do is share chapter 10 first, and we'll see if there are any questions on 10. There we go. And let's make it a little bit bigger. Maybe boost it some so we can see it better. Okay. So any specific questions on chapter 10 that we need to address?
I have a question. There is a question on chapter 10's homework that I've done 3 examples of already, and I'm still getting it wrong.
Oh, okay.
Can I send it to you?
Yeah, OWL has a facility for you to send the instructor a question regarding the homework problem. But let's see. I'm going to try something. Let's stop this share. And let's see. See if I can get to it from here. So if I go into Blackboard, back up. Come on. I'm going to have to go in this way. And there we go. What I'm aiming at is to to give everybody an opportunity to get the benefit of our discussion. Go. Let's see. Science. There's chapter 10, and there's the homework. Let's look at it as student and see if that helps. Okay, do you remember which question it was? These are not supposed to be randomized, so it should be just whatever question number.
I can pull it up on my phone real fast and look.
Okay. That's the trouble with these online homework assignments. The expert system that controls them is sometimes very unforgiving in your answer. You can be off by a single digit and it'll tell you it's wrong. Whenever possible, I try to build in a uncertainty region so that if something like a rounding error or something that's not critical to answering the question doesn't give you a false response. Let's see, if we were going to, okay, here, email instructor at the bottom.
Mm-hmm.
So anytime you have a question about a specific question, then you can email the instructor, and that way I will get details from the question itself. Did you find it yet?
It's loading. Where I've got my iPad sitting right here, my iPad's on the Wi-Fi, so I had to turn my phone off the Wi-Fi.
Oh.
I hate technology.
It's a double-edged sword. When it works, it's great. It can make you more productive, but when it doesn't work, things come crashing down.
Let's see. It's number 10.
Okay.
For some reason, the way that I'm doing it, every time that I've done them, I have had to do them a couple times because it keeps telling me the way that I'm doing my atomic radius is wrong. And I don't get how.
Okay.
Like my math matches pretty much, but
Cubic closest packing with an edge length of, okay. The first possible error here is what do they mean by cubic closest packing? Cubic closest packing, we need the interpretation. What does that mean in terms of, is it a body-centered cube? Is it a face-centered cube? It's most likely a face-centered cube, which gives you if I can remember, which gives you a different formula for the edge length. And that should be in your useful information. Okay, here's body-centered cube. Where's face-centered cube? edge length. Don't tell me I left it out. We had one like this in the PowerPoints, did we not? I'm pretty sure we did.
My biggest struggle is finding the atomic radius. I don't.
Calculate the value of the atomic radius. Right, it's a calculated form and the density. You need to know the atomic radius. All right, let me call up that on my other computer here. I want to call up the PowerPoint slides because I think we did have.
It tells you how to do it.
Oh, does it give you suggestions?
Yeah, it tells you how to do it step by step.
So if you put in the wrong answer.
Yeah,
right,
if you put in the wrong answer, it'll show you what you did wrong. But when I go to another one and I try to correct it like the same way, I'm still doing it wrong. And I don't know if like my numbers are just off, like maybe by like 1 or 2, and that's why it's counting it wrong. Because I mean they're pretty close. But I mean, I don't know. It's just question number 10. I'm getting the density correct and everything. It's just the atomic radius that I keep getting wrong.
Okay, the atomic radius. We have to use the right formula for that one. Here it is.
Yeah.
So this is a body-centered cubic. No, face-centered. That's the face. Right, it is the face-centered cube. The length of the diagonal is 4 times the radius. Right, so you need to know the diagonal. If you know the length, you can find the diagonal, right? Because of Pythagoras' theorem. Right, this side squared, that side squared, add together is equal to this side squared. This side squared is actually 4 radii. There's 1, there's 2, there's 3, there's 4. So there's your 4r squared. Right, then the solution gives you the length of the side of the cube divided by the square root of 8. Did you do it that way?
I think I know what I'm doing wrong now.
Okay.
So I'm looking at it.
But do you think it may just be a math error?
Yeah, I think what I did was, because on here, like my number on here, it says with an edge length of 393, and I don't think I divided correctly.
Okay.
I think that's all.
You also have to watch your units.
Yeah, I think that's all that I did wrong.
Right. So the atomic radius is in meters. Right. Sometimes it gets strange with that also. If you put in scientific notation, it has to be exact. Okay. Anybody else with the homework while we're here? We'll go back to the review document then. I could just unshare this and leave it there, and then reshare this one. Okay. We're still in Chapter 10. Any problems with Chapter 10 review? Nobody's having problems with chapter 10? Okay. This may be a short session. Let's see if I can find ones that have given students trouble in the past. How about number 7? Which of the following compounds has the lowest viscosity? So low viscosity means it flows easily, right? If something flows easily, then the intermolecular forces should be less. They should be the least. So you would expect the lowest viscosity to not have any polarity first, and to minimize London dispersion forces, right? So that means we can discount hydrogen chloride because it's polar. We can discount water, it's polar. Then we have to consider the nonpolars, carbon tetrachloride, nitrogen gas, and this monster right here. That's a large aliphatic hydrocarbon. Remember what we were discussing with the, when I was describing long chain, these long chain aliphatic hydrocarbons. The longer the chain, the higher the boiling point. It also leads to higher viscosity. So these guys, this one would have very high viscosity. So you would discount that one based on that, and then you would go to carbon tetrachloride versus nitrogen and look at the London dispersion forces there. But remember, these bonds are still polar. Even though the whole molecule is nonpolar, you still have a slight displacement in charge between the carbons and the chlorines. So you still get the potential for increased attraction, even though they're nonpolar. And the dinitrogen certainly has no polar bonds, and it's symmetrical. So I would expect the lowest viscosity to be associated with the nitrogen gas. And then the other way to look at it is, once you've narrowed it down to gas versus liquid, right? What's the viscosity of a liquid versus a gas? Liquid's always higher viscosity than a gas. How do you explain the convex meniscus of a liquid? What do we mean by convex versus concave meniscus? Well, in order to have meniscus, your liquid has to be in some kind of container, and it has to be narrow enough to show it. If you put a liquid into a large beaker like this, you're not going to see a meniscus, right? Because the interaction between the liquid and the container is right out here on the edge. And by the time you get out here, things are flat. So you need a narrow container. A small glass tube. This would be concave, this would be convex, right? So we're particularly interested in this one, the convex. So how do you explain that in terms of competing attractive forces? Well, what are the attractive forces that are competing? The adhesive forces are what? Adhesion is between dissimilar molecules. So the adhesion would occur between the liquid and the glass. and the other is cohesion, or cohesive forces. Those are the ones that attract the molecules of the liquid to each other. So that being the case, which one of these wins, so to speak? The cohesive forces are stronger attractors than the adhesive forces. So that would be B. The cohesive forces are stronger than the adhesive forces. Isaac is here. All right. Okay, where is he? There's Isaac. Everything okay at home?
Yeah, I got it lined up.
Good checkup?
Yep.
Okay.
Well, thank you.
Okay, we're still in chapter 10. And nobody's actually having problems. So I'm just sort of talking through some things, trying to anticipate things that might give you a problem under the heat of exam, heat and pressure of exam. Here's an interesting one. Number 12, which of the compounds below is not an example of a molecular solid? Well, let's define what a molecular solid is. Well, first it has to be a solid, right? What do we mean by molecular? Molecular implies covalent bonding. Because a molecule is a collection of atoms bound together in such a way that when they interact with one another, the bonds between the atoms are not disrupted by the interaction between one of those groups with the other group. So you have to have the strongest possible bonds between the atoms, and those are covalent. So what other types of bonds do we have? Well, ionic, of course. Those are the next strongest. These are the strongest. These are the next strongest. And then we have dipoles. And then the least strong are the London dispersion. Okay, so if we look at that group and use good test-taking techniques for multiple choice questions, by the process of elimination, what we try to do is eliminate those that are not molecular. Right? So is I2 a molecular? Right? Actually, it is. All the diatomics are molecular. And what are the diatomics? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are all moleculars. Now, this one is a solid at room temperature. That one's a liquid. And the rest of them are gases. So the diatomic iodine is a molecular. So we have to keep that one. How about silicon dioxide? Silicon dioxide is an ionic compound. So we can throw that one out. Carbon dioxide is a molecular solid. And it's going to look like, I could do your Lewis diagram, your Lewis structure. That's carbon dioxide, right? So you've got covalent bonds. It's molecular. How about water? Water's molecular, right? Right? They're your covalent bonds. And C25H52, which is that same molecule we looked at earlier, long chain hydrocarbon, that's molecular. So which of the compounds below is not an example of a molecular solid, right? That they're all molecular except that one, right? Silicon dioxide. Silicon dioxide is an ionic compound. What is silicon dioxide? What's an example? Right? Walk on any beach. You got lots of silicon dioxide between your toes. It's sand, as an example, right? There are other places you can find silicon dioxide, but that's definitely a good place to find it. So that's the one that's not a molecular solid simply because it has no covalent bonding. Those are ionic bonds. Okay. This one might trip you up also. A solid crystal of sodium chloride. What is a solid crystal of sodium chloride? What does it look like at the atomic level? It's an ionic solid, right? So you have a matrix, a crystal structure with the positive and the negatives in the crystal. So then you look at your choices and just take the first of each one and say soft or hard. Well, solid crystal sodium chloride is hard. That's characteristic of ionic solids, right? So you can eliminate A, you can eliminate C, you can eliminate E. So it's either B or D. Then high melting. Are ionic solids typically high melting point? Yes, very high melting point. Thousands of degrees, usually in that neighborhood. At least 1,000, usually more, centigrade. So both of those say high melting, B and D. Good electrical conductor, poor electrical conductor. What does it take to be an electrical conductor? You have to have mobile charges. Emphasis on mobile, right? These ions have to move in order to conduct electricity from one side of the crystal to the other. Can they move? No, they're locked in place. So a crystal, a large crystal of sodium chloride, is a poor electrical conductor. In fact, it's an insulator. Right? So that makes D the only possible answer. Could we make sodium chloride a good conductor? Sure. Put it in solution, dissolve it in water, and that would break up this crystal structure and you'd have free ions. You stick 2 electrodes in it and you get a light bulb lit. So that's key, the electrical conductivity of the solid ionic versus the liquid ionic or dissolved ionic. Now, if you melt it, you get the same result. Well, similar result. You get electrical conduction because the ions are now mobile. Okay, which of the following has the highest melting temperature? Well, we look at, well, I erased it. We look at the order of the strength of bonds. Covalent bonds hold things together. So if you take a solid that is molecular and heat it, you will get it to melt, but you will not disrupt those bonds, right? So we can discount for this purpose the covalent bonds. What if you break the covalent bonds with heat? You don't have the molecule, you don't have the compound anymore, right? So that doesn't count. We want to change phase, not chemical reaction. So we have to discount any disruption of covalent bonds, right? So high melting temperature. What's the next possibility? Ionic bonding. So you look for ionic solids for high melting temperature. In that case, we have magnesium fluoride. That's the only ionic compound in there. The others are covalent. And the forces that they have available are either dipoles or London dispersion, which are not as strong as ionic, and consequently give you lower melting temperatures. Now you can interrupt me anytime if we, in the discussion, if something just pops into your head and you have a question about it, please stop me. How about this one? At normal atmospheric pressure, and that we must assume is 1 atmosphere, and a temperature of 0 degrees, which phases of water can exist? Remember what the phase diagram looks like. Right? Triple point. And we have one going this way, and we have one going this way, and we have one going that way, going this way. So here's your solid, here's your liquid. Oops, don't need that. Here's your gas. So at 0 degrees, where are we? Well, we're over here somewhere. So at 1 atmosphere pressure, at 0 degrees, you're on that line between solid and liquid. So at 1 atmosphere and 0 degrees, you can have 2 phases of water that exist, both the solid ice and the liquid water. That's why A is the answer for this one. And I'll repeat, anytime you have 2 phases together of any, well, let's stick to solids and liquids in this case. If you have the solid and the liquid, and they're both together at the same time, then the temperature will be the melting temperature for the solid, or the freezing temperature for the liquid, same thing. And as long as both phases are together, they will be fixed at that temperature. So at 1 atmosphere pressure, 0 degrees centigrade, you have a solid and a liquid. And until the ice completely melts or all the water freezes, you're going to have 0 degrees, and it will not move from that point. Okay. Here's one thing that we spent a little bit of time in lecture on it. But processes that occur, and I probably should have left that up there. Let me make it bigger. So this is just a theoretical, that's the triple point. Okay, so if we have a solid, liquid, gas, crossing those boundaries we have terms that apply to crossing those boundaries between the phases. So if we cross from solid to liquid, that's called melting. Okay. If we cross backwards, that's called, we have a couple of terms that we use there. This is called either freezing or fusion. Okay. If we go from liquid to gas, let's see. Let's say we're holding the pressure constant and we're moving from here to here. So we go from liquid to gas. That's called boiling, right? Or evaporation. Right? We go backwards. That's called condensation. Okay. Now, what else do we have? We could go from solid to gas, right? That's called sublimation. If we go backwards, that's called deposition. Okay. So those processes that go from one phase to the other, they all have names. And we're referencing them here. So which of the following processes must exist in equilibrium with the evaporation process when the measurement of vapor pressure is made? We measure vapor pressure, we're going from liquid to gas. Right? So they must occur together and they must balance for an equilibrium to be established. So evaporation has to be in equilibrium with condensation. Okay? Has anybody looked at these documents? Yeah? Okay. Well, that's good to know. I'd hate to think that I went to all this trouble and nobody even looks at them. Let's see. We could probably go another 15 minutes on this chapter and then we'll switch over to chapter 11. While we're on the topic of these processes, which of the following processes will energy be evolved as heat? In other words, exothermic process. Think about what's happening. If you're decreasing the energy of the system, in other words, the molecules are becoming lower energy as a system, and their attraction with one another is stronger. That means that the energy that may have been applied to separate them is now gone. So that's being expelled. It's exothermic. So if you go from a gas to a solid, you should release heat. If you go from a gas to a liquid, you should release heat. If you go from a liquid to a solid, you should also release heat. Those are all exothermic processes. So we just have to pick the one here that applies to, well, there's one that I left out. Let's see, sublimation is going the wrong direction. Vaporization, going the wrong direction. Melting, going the wrong direction. Crystallization. What is happening? This is one process that doesn't fit this scenario. So what happens when a crystal is formed? Well, you're going from, I'm going to this is sort of a teaser to entropy. When we go from disorder to order, and crystallization is an increase in order, we're decreasing the energy of the system. When you go from loose ions to our regular structure, you're actually increasing the order and decreasing the amount of energy that's stored in the system. So that means you have to release energy. So when something crystallizes, energy is being released. That's why the answer to this one is crystallization. Now, I can't remember if the authors discussed it in those terms. But if they didn't, they should have. Okay. Let's see. Let's pause for this one. So what we're saying is the normal boiling point of a liquid X is less than Y and is less than Z. So the boiling point of X is less than the boiling point of Y, which is less than the boiling point of Z. What does that say about the intermolecular attractions? If the boiling point is less for this one, then the strength of attractions among the molecules is less for this one. So that's just abbreviated force. So the force of attraction there, let's see. That could be fluorine. So let's say intermolecular force, IMF, impossible emission force, is less than this one, is less than that one. Okay, so now that we know that the attractions are less for X than for Y than for Z, we can say something about the vapor pressure of the three liquids. So what happens when the force of attraction increases, the vapor pressure decreases, right? So in this case, the vapor pressure here for X should be greater than the pressure for Y and greater than the pressure for Z. Remember, that's the only one that works in reverse. As you increase the intermolecular forces, this one actually decreases. Why? Because there's less attraction among the molecules, and at the same, with the same value of input of heat in terms of temperature, you get more of them leaving the surface of the liquid and increasing the vapor pressure. So that's why, let's see, the order of increasing vapor pressure, Z to Y to X. So Z to Y to X answers that question. Okay, let's take another look at, how about this one? So here's a phase diagram for some compound, and you want to purify the compound or purify your sample by subliming it. Right. So, well, let me just use the existing. Let me blow it up a little bit so we can see it better. And let's make it even bigger. There we go. So, in order to sublime the sample, you should do what? Well, what do we mean by sublime? Go from solid to gas. So you have to know how to interpret a phase diagram. Where are the solid, liquid, and gas areas? Well, the solid is here, liquid is here, gas is here, right? So to sublime it, we have to go from this area to this area. So the conditions that are given are okay, if we're starting, we've collected the sample at 1 atmosphere pressure, so we're right here, and 100 degrees K, which is here, so we're right there. So how would you sublime the sample? Well, you could maintain that temperature and just decrease the pressure, right? If you decrease the pressure far enough, right, you're in this region. But is that one of our choices? Well, let's take them one at a time. If you increase the pressure to 1.5 and then increase the temperature to 300, where's that going to put you? 1.5 and 300, that puts you over here. You're not subliming the sample. Now, if we increase the temperature to 300 and keep the pressure at 100, same problem. You're not subliming because you've got to go through liquid to get to gas. Right? That's not subliming. That's melting then boiling. We want to go straight from solid to gas. If you lower the pressure to 1/2 an atmosphere and then increase the temperature to 200, what's that? Now you're crossing that boundary right there. That answers the question. You can stop, move to the next question in the test. Okay, let me bring it back down again. All right. Well, let's see. These are a little bit more difficult questions. I didn't realize I was staying in the easy ones for so long. All right, number 4 is going to require some calculations. Right, so, and this is number 4 in the moderate section. Let's see. Here we go. Ask yourself, what do you need to know to answer the question? The resulting sample contains which of the following? In other words, when you have this much energy added to this much water while it's ice at 0 degrees, then what happens? You watch the temperature change because we haven't changed the pressure. There's no indication that the pressure's changed, so we only have to deal with temperature. So here's what we're looking at. Okay, so as we temperatures on this scale, and this is just progress. So as we heat, right, this is ice, and then when we get to 0 degrees centigrade, it stops. And here we have ice and water, liquid water. Right. So the temperature is constant. Then when all the ice is gone, we start heating the water again. So now we only have liquid water. Then when we reach 100 degrees, we've got liquid water and gaseous water, steam. Then when all the liquid's gone, we can heat it again. Right? So now we have steam. So when you're doing calculations, there are different formulas involved here. And I don't think we talked about that. We actually covered that in calorimetry in the first semester. When you heat ice, you've got the amount of heat, delta H, let's see, for this one. You have your specific heat, you have your mass, and you have your change in temperature. Okay? So this works for any of these sloped lines. Okay? So you have one for this one with a different S, and for this one, you have a different S. And then for these in here, you have heat of fusion. So for these, where you're, for the phase changes, you have a certain amount of heat, but here all you need is the mass, and then you need the specific heat of fusion. For this one, the specific heat, oh, they call it the latent heat. The latent heat of fusion here, or the latent heat of vaporization. Okay, so that's for these flat ones. So the way to structure the analysis of this problem is, if you're starting here at 0 degrees, I think that's where we're starting, water as an ice sample. So you've got pure ice right here, and you're adding heat to it, 12,500 joules. So what's going to happen here? Well, you're going to start melting it. So that means you're going to use this one first, right? So you've got 36 grams, and the heat of fusion is 6.02 kilojoules per mole. So we need to use moles, right? So you do the calculation for this one using that with 2 moles and 6.02 kilojoules per mole. So for this one, how many joules are you going to use up if you go all the way across? 2 times 6.02 is 12.02 kilojoules. So you've got 12,500, or 12,040, right? So you've got 460 joules left over. So what do you do with the 460 joules? Well, now you use this heating curve here, and you need the specific heat of water, which is 4.18, times so many grams, which was 36 grams, and then change in temperature. So what's the change in temperature? Well, we don't know, but we do know how much heat is left over, right? So 4 times 36 is what, about 140. So you divide 140 into 460, and you get roughly 3, between 3 and 4 degrees centigrade, right? And 3 to 4 centigrades takes you from what? From 0 to 3 or 4 degrees. That's right. So you're still liquid, but there's no solid left. You've melted it all. Right? So that's as far as you need to go to answer the question. You have only water. There's not enough heat to go to steam, and all the solid's gone. Okay? Is that confusing enough for you? See, we didn't do this type of problem in class, in the lecture. So that's why these review documents are good. This is actually application of what we learned in theory. And that's an example of a problem that's on the surface appears complex, but the way to solve it is to break it down into small pieces, which we did. Okay. So let's look at maybe a difficult one. All right, this difficult one is going to use what do we need to use to solve this one? Anybody heard of the Bragg equation? This is solved with the Bragg equation. I see number two. Number 2 looks like the problem that we were looking at earlier with silver in the homework. Let's see. So let's go ahead and do this one. So how do we deal with this type of problem where we know we're going to have to do a calculation? You go into the wording of the problem and extract information. Right? So we're analyzing a crystal with X-rays. That's good. What's the wavelength of the X-rays? 2.33 angstroms. So the wavelength of the X-ray is 2.33 angstroms. Okay, there's our first problem. Using the equation with, well, actually, it's not a problem. Why? Because we know we're going to need the Bragg equation. So we need this. And the Bragg equation should be, I'm sure, it's in your useful information. So there's our wavelength. Let's see, is it going to be a problem? No. Why is it not going to be a problem? Because wavelength in angstroms and distance between the layers also in angstroms, right? So that means they cancel out and we can use the same wavelength. We don't have to convert that to meters, right? Some calculations you need to convert to a standard value, a standard unit, right? But in this case, we've got a ratio, angstroms on that side, angstroms on that side, so we don't have to mess with it. Okay, let's get some more information out of this thing. First order diffraction, n equals 1. So what goes with n equals 1? The angle of the X-rays goes with first order at 19.2. There we go. So what would the angle for the second order diffraction be? That's the question. Now we've extracted everything out of this problem that's available. And the question now is, how do we determine this one? What can we get from what we already know here? Well, we've got that one filled, we've got this one filled, that's standard, and we got this one. So we can solve for the distance between the layers, right? And the distance between the layers is not going to change when we move to this solution, right? So if we have this value for the second part, we solve it for the first. The second part, we got this. We've still got the same wavelength, right? That hadn't changed. Now we have a different value for n, second order. Then we can solve for theta. Okay. So if we plug these numbers in, 1 times 2.33, and then 2 d sine 19.2 degrees. Right, so you need a calculator that'll do sines. What does d turn out to be? Oh no. Yes, that's right. D, to shorten the time we spend on this, d is 3.54 angstroms. Okay, so now we can pull it down to solve this problem. We've got 2, and the wavelength is the same. See, I'm being kind. We could have combined these two equations and done it in one solution, but I'm doing it in 2 steps because I think it might be easier to understand that way. Okay, then we have 2 here at the same distance, right? And then we have sine theta. So now we've got one unknown, and we can solve for this one. So these two are going to cancel. This one's going to be like that, sine theta. Okay. So how do you solve for theta on your calculator? Well, at least on my calculator, we have a function key, and for the sign above it is the arc sign. The arc sign is like go in the opposite direction. It's not the inverse, it's the, let's see, what's the right term? It escapes me. But if we do that solution, 2.33 divided by is 0.658. Then if you put that in your calculator and do the arc sign on this number, you get theta. In that case, theta is 41.2. So what do we mean by order? Has anybody had physics? Nobody's had physics? Order references the, oh, here's a good example. You ever seen a rainbow? Everybody's seen a rainbow, right? Okay. If you catch a rainbow at just the right time and viewing angle, how many bows do you see? Usually you see 2 or more rainbows, right? But there's a really bright one, and then the second one is a little fainter, and if you're lucky, you'll see a third one that's even fainter still. The bright one is first order. The second one is second order, third order, and that is a consequence of the laws of diffraction, where you get constructive and destructive interference. You can get constructive and destructive interference at more than one point in the in the interaction of the waves, right? And in this case, the angle occurs 19.2, and in the second order, it's at a steeper angle. Okay, so that's the short version of what order is. All right. That was the Bragg equation, and how to deal with the Bragg equation. Let's see. We got about an hour, and we've still got chapter 11 to look at. Let's see. Let me stop this share and we'll go to chapter 11. Assuming there are no questions on chapter 10. Chapter 11, share. So that's pretty good size. Let's boost it up a little bit. Here we go. Okay, the easy ones, we might not even have to spend much time on the easy ones. Anything particular in chapter 11 that's bothering anybody? In the review document, in the homework, everything's fair game.
Actually, I have a question in number 1.
Okay.
For the mole fraction, did you use the density for water?
You use what for water?
The density to find the mole fraction?
Let's see.
Because I look into your how to do it page, and you have 0.9970 over 1 milliliter.
Yes. Yeah.
Ah, okay.
That's the actual density up in
Of the
the
water.
yeah. When we were discussing this in the lecture part of the series, we generalized a little more and just called it 1 gram per milliliter. But
Okay, gotcha.
that's actually the density of water. It's not 1. Now, when is the density of water 1 gram per mil? There's one temperature at which that is true. That occurs
Okay.
at 4 degrees centigrade. Maximum density of water is 1 gram per milliliter at 4 degrees centigrade.
Okay.
So as water is cooled, its density increases to that point, and then from 4 degrees down to 0, its density starts decreasing, because at that point you start to organize the hexagonal structure, and that makes it expand. So this is maximum density.
Okay.
We'd have to be exactly 4 degrees to use that one.
All right.
Okay, so when we did all those calculate-divs, everybody understand how each of these calculations was done to answer question number 1. Well, if you have a 0.1 molar solution of sodium chloride, which of the others would be closest to 0.1? Well, the way I solved that problem was to actually calculate the concentrations, convert molar concentration to these various forms. But logically speaking, when we say, what was it, 0.1? Yeah, 0.1. 0.1 moles per liter. If you press for time, 1 liter of water is pretty close to 1 kilogram. So if we substitute a kilogram here, and for dilute solutions like that, while this is liters of solution, and this is kilograms of solute for molal concentration, the actual number doesn't change that much. So molar and molal are very close to one another. So that's one way to get the question answered correctly without spending a lot of time on it. Okay. So how do we answer number 2? Which of the following concentration measures will change in value as the temperature of the solution changes? The key to that one is which ones involve volume. Because if you change the volume, if you change the temperature, you're going to change the volume of your liquid. And mass percent has no volume in it. Mole fraction, there's no volume there. Molality, that's only mass, no volume there. Molarity is the only one with volume in it. There's your answer. Let's see. Number 4 might give some people trouble. Which statement about hydrogen bonding is true? We'll just define what hydrogen bonding is first. Right? Hydrogen bonding is a special case of dipole. In order to have a dipole-dipole interaction, you just need 2 adjacent molecules to have a dipole moment for the molecule. And if the molecule is big enough, you only need dipole moment for individual bonds. But for small molecules like water, the whole molecule needs to have a dipole moment. And water does. Let's see. But we're not talking about water, excuse me. We're talking just about hydrogen bonding. So hydrogen bonding requires that you have hydrogen on one end of the bond and an electronegative, a highly electronegative atom on the other end of the bond. And that usually means, let's see, can't see that. That usually means oxygen or fluorine, or what else did we say? Nitrogen, fluorine. I think sulfur would fit in there also. Because remember our periodic trends, the highly electronegative atoms are way over here. But they have to be sufficiently different from hydrogen. Different from hydrogen in order to give you that dipole moment and contribute to hydrogen bonding. So let's get back to the question. A says that hydrogen bonding is the intermolecular attraction forces between 2 hydrogen atoms. No, you have to have something different than hydrogen. And in fact, if you do have a situation where a molecule, say, has an oxygen and a hydrogen, you're going to have this, where you have slightly positive here, slightly negative there. You need another molecule. If the molecules are small, you need another molecule where the hydrogen orients itself in such a way as to give you an electrostatic attraction, right? So it's not between the two hydrogens, it's between the hydrogen and the electronegative atom. So A's out. The hydrogen bonding, B, the hydrogen bonding capabilities of water molecules cause that 4-carbon atom to be more soluble in water than, it's just the other way around, right? Because for this molecule, there are no electronegative atoms bound to hydrogen. You do not have the dipole moment sufficient to form a hydrogen bond. Whereas with this one, which is what? Methanol, you do have. You have your CH3, and then you have here, right? So this gives you the dipole moment for forming hydrogen bonds with water. So that's why methanol is particularly soluble in water. In fact, most small alcohols are soluble in water for that reason, because they have this capability of hydrogen bonding with water. So B's out. C, hydrogen bonding of solvent molecules with a solute will not affect the solubility of the solute. That's false on its face. Anytime you have the capability of hydrogen bonding, you increase the solubility of the solute in the solvent. Why? Because the dipole-dipole interaction with hydrogen bonding involved is much stronger attraction than just general dipole-dipoles. D, hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecules. That's also false. The strongest bonds between atoms are covalent. Nothing is stronger. So everything else is below that. And when you say hydrogen bonding is stronger, then it's false on its face. So by process of elimination, that means E has to be the answer. Hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. That's true. I wish they had been more specific with this, but it's still true. And the best answer compared to all the others, which is the other rule that you follow when taking my exams. If you don't find one that's exactly perfectly right in your mind, go for the best one. So for 5, let's see, we're still in the easy section, aren't we? For 5, which of the following favors the solubility of an ionic solid in a liquid solvent? Well, let's see. Is A true? A large magnitude of the solvation energy of the ions. So what do we mean by solvation energy? The solvation energy is a measure of how much energy you get back. How much do you lower the energy of the solution relative to the energy of the individual components. So solvation energy, if it's large in magnitude, says you get a lot of energy back when you form the solution. And like I said, with all natural systems, they tend toward lowest stable energy point. So you decrease the amount of energy of the system, you produce a more stable system. That increases the probability of forming that particular association, in this case, a solution. A small magnitude of the lattice energy of the solute. So what's the lattice energy? Well, the lattice energy is a technical term lattice energy, let's see, it would be in terms of delta H, lattice. Lattice energy requires specific conditions. So the individual, let's restrict our discussion to ions that form a crystal lattice. Okay. So the individual ions, positives and negatives, have to be in the gaseous state. And then they have to come together to form your solid crystal lattice. Okay? The amount of energy, and the lattice energy is actually reverse of that. The amount of energy required to produce gas from that solid. Right? So that's what the lattice energy is. If the lattice energy of the solute is small, then it doesn't take much energy to break them up, and it's easy to get them in the solution. Right? So A and B are both true. So, and a large polarity of the solvent for an ionic solid will produce a stronger attraction. Remember, the polarity of the solvent is a slightly polar nature, or well, actually a large polar nature, which contributes to electrostatic attraction. So the larger the electrostatic attraction potential of the solvent, is more likely to produce a solution with a solute that's ionic. So in fact, all of those statements are true. Let's see, how are we doing on time? Okay, we got about 50 minutes, and we're still in the easy section. Yeah, we're still in the easy section. Number 6 might have given people trouble. Let me ask myself a question here and see. Just a second. All right, we do need to deal with this one. So, since we were talking about lattice energies, this will be a good place to go for our next one. This number 6. So, what information are we given? All right, so let me use the correct. Solid KF has a lattice energy. Solid KF has a lattice energy of negative 804 kilojoules per mole. You know, now that I look at it, the negative value means what? It means as those gases come together, to yield the solid, it's giving up energy. So actually the value, is, I had it right the first time. Going this direction is negative. Large negative value means a lot of energy is given up when this solid forms from the gaseous atoms, ions, from K and F minus. And the heat of solution of minus 15. So what's the heat of solution? Well, if the KF solid becomes KF aqueous, which means individual ions in solution. There's also a value associated with that, and it's minus 15 kilojoules per mole. That's for KF. For rubidium fluoride, right? So let's get oriented here. So they're both fluorides. So there's the fluoride. Potassium fluoride is here. Rubidium is in the same family. So for rubidium fluoride, the lattice energy rubidium fluoride, the delta H lattice is equal to minus 768 kilojoules per mole. And the heat of solution equals minus 24. Okay, so that's all the information we can get from that. So the question now is, which salt forms a stronger attraction with water? So what are we talking about, a strong attraction with water? What we're looking at is the, this goes back to, let me erase this because I don't want to erase all that stuff. This goes back to our discussion of the what's involved in forming a solution, right? Those three processes. Right? So this would be where you break the solute apart. This is where you make holes in the solvent, and this is where you the attractive force between the solute and the solvent takes effect. Right? So the question is asking us about this one. Which one has the stronger attraction? Let's see. So this one refers to this process here. This process and this process. In other words, if the lattice energy is negative 804, that is, if you're going from here to here, you have to add that much energy back, right? So you're actually changing the sign of this, which would be the negative delta H lattice. In other words, you want to make that a positive value to fit this scenario. The heat of solution is given here, right, as a value, right? So we've got that one for each process. We've got this one for each process, and delta H2 and delta H3 then refers to, excuse me, this one is going to be the same for both of them. Delta H2 is the same because it takes the same amount of energy to pull the water molecules apart. Right? This one changes. So really all we need to do is compare that together, because this is going to be the same for both. The only difference between the values will be this one. So if we can solve for that one, we can determine, we can answer the question, which is the, which salt forms the stronger attraction. So what we want to do is solve this equation for each one. And let's see, I guess I'm going to have to erase. Okay, so we've got three terms in here. We have to apply a negative to this one. And if we solve for that one, what are we going to call that? Well, let's call it delta H of hydration. That'll include both the making the holes and the attraction of the solvent and the solute. Right, so now we have three terms. We want to solve for this one. Delta H of hydration then would be equal to delta H of solution plus delta H lattice. Right, so now we've changed this sign back to a positive. So this is going to be whatever the value is, negative, and this is going to be also negative. Yes. All right, so what do we got for the first one? Well, the first one, the delta H hydration for KF, the delta H of solution is what? It's 15, minus 15. I'm not going to put the units in it because I don't have a lot of space. And then we have negative 804. So what's that? Negative 819 kilojoules per mole. That's the heat of hydration. Delta H for rubidium, all right, then would be what? Minus 24. And then 768. Which would be minus 792. All right. So now we've got numbers we can compare for the heat of hydration. So when these things come together, you get that much energy out of them. Right. So what that says is that the attraction is stronger for KF with water than it is for rubidium fluoride in water, right? Because this is a larger negative number. And that makes the answer C, since it has a more negative heat of hydration. Right, so we actually had to define terms. The heat of hydration incorporates the second and the third process. Okay, did I confuse you? Or maybe it makes sense now, but when you go away and look at it again later, typically what happens is you say, what did he say? So fortunately, I did remember to start the recording. So you can go back and look at the explanation again.
There's this problem on the homework.
I'm sorry?
There's a problem like this in the homework.
Oh, okay. Okay.
Yeah.
Did they describe it the same way?
Yeah.
Good, good. That's good to know. Because I want to be.
They use
what?
balanced chemical equation. They use balanced chemical equation and then use the formula, like how it relates to the formula.
What chemical equation?
Balanced chemical equation.
Oh,
Like they just have it diagrammed, so like, and then equal it to the formula. But yeah, it's the same.
so they did give a little more detail.
Yeah, yeah.
Okay. All right. Let's see. How are we doing on time? We got 35 minutes, and I'm still in the easy section. Let's see. So what happens when we push that piston down? Well, Le Chatelier says we're going to disturb the equilibrium, and how does it respond? It responds by reducing the number of molecules in the vapor phase, and they go into solution. Right, so we're going to increase the concentration. Well, let's see. Hold on a second. Are we forming a solution? Yes, those circles are supposed to be gases that are different than the molecules that are that form the solvent. Right, so as we increase the pressure, we're going to drive more of these gas molecules into solution and increase the concentration of them in the liquid phase. So that's why C is the answer. This will cause the pressure of the gas to increase and the concentration of the dissolved gas to go up. One thing about it is while the concentration of the gas in solution does increase, the pressure in the headspace is also increased. It's not increased as much as it would be if you had a pure gas that was being pressurized, because some of it's going into solution. But you do increase the pressure in the headspace still. It's just that the final equilibrium position places some of that gas in solution in order to reduce the pressure in the headspace that would have developed. And then you reestablish your equilibrium between the dissolved gas and the headspace gas. All right, let's see. What's Henry's law? Remember Henry's law? The concentration of a gas depends upon the pressure and some proportionality constant. So that would be none of these. The concentration of a gas in solution is inversely proportional, no, to the temperature. It says nothing about the temperature. The concentration of the gas in solution is directly proportional to the mole fraction of the solvent. No, it doesn't say anything about that either. It doesn't say anything about mole fraction. Concentration of the gas in solution is independent of pressure. Oh, that's false, right? Proportional to the pressure. Concentration of the gas in solution is inversely proportional to the pressure. No, it's directly proportional to the pressure, right? So D would have been the right answer if it said directly proportional rather than inversely proportional, but it didn't. So none of these. That's Henry's law. Now, Raoult's law does say something about the mole fraction. Right? So what does Rayleigh law say? Because I think that one's coming up next. Yeah, 10. Rayleigh's law says that if you know the partial pressure in the headspace of the pure liquid, then in order to solve for the actual pressure, you need to know what's the mole fraction. What's the mole fraction of the solvent, right? So we formed a solution and decreased the mole fraction of the solvent. So this pressure should be less than that pressure because that is a fraction. Okay, that's Rayleigh's law. And this one works if the solute is non-volatile. Right? In that case, the solute has to be non-volatile. If, however, the solute does exhibit some volatility, then we have to modify Rayleigh's law to incorporate both of them. So the final pressure then, you need to know the pure pressure for the solute and the solvent, and then take into account the mole fraction of each. Then when you add them together, you get the total pressure. And that's because of what law? Dalton's law of partial pressures. Now if we go to 10, if a solution contains 1 mole of liquid A and 3 moles of B, the solution has a vapor pressure of 314 torr at 25 degrees. Okay, so we're holding the temperature constant. That's good. Liquid A has a vapor pressure of 265 and liquid B has a vapor pressure of 355. Which of the following is true? Well, the question is asking you to compare the reality with the ideal Rayleigh's law, right? So if we do that, what we have is a diagram of increasing A and increasing B this way. So as A increases in its mole fraction, actually, mole fraction of A, mole fraction of B. If A mole fraction increases this way, then as a pure liquid, we're going to get ideal, right? So this is 1 and this is 0. For B, then we might get something like this. So for B, it's going to be 1 here and 0 there. So the combination then is connect those two. Now that's the ideal, where you have straight lines here, straight line there. And the summation of the pressure at any one point is this one plus that one. Okay, so can we say it's ideal in this case? I mean, if we could say it's ideal, then it's C. So what would we need to know? Well, let's gather our information. So if we have 1 mole of A and 3 moles of B, A is 1 mole, B is 3 moles. So what's the mole fraction of A? The mole fraction would be 0.25, right? Because it's 1 in 4 total. That means this one has to be 0.75. Okay, that's given. So the solution has a vapor pressure of 314 total. So let's see. A would be low. B would be high. So this is about the position, right? So at that point, our vapor pressure is 314. Okay. Now, the individual pressures are 265 for A and 355 for B. Wait a minute, that's not right. A has a vapor pressure of 265 and liquid B has a vapor pressure of 3. Oh, okay. Okay. So if this is 355 for B and 255 for A, 265, excuse me. Right? If it was ideal, we'd add those two together, right? But it's not ideal, is it? In fact, we would expect over 600 torr, but we actually only have 300. So what's the deviation? It's negative, right? We have a negative deviation because the total is much, much less than the sum of A and B. Well, actually, we didn't do the mole fraction, excuse me. That's not right. This would be the pure times, let's see, this is A, so this would be 0.25. And this would be times 0.75. Okay, I'll jump the gun. My apologies. So this will be 266, which is due to that one. And 265. This will be 66, roughly. So now we add those two together. So that would be 2, 3, let's see, is that right? 332. This is what we would expect under ideal conditions, 332. If we apply the modified Reynolds law. But we're only getting 314. Okay, so that's a negative deviation. Did I confuse anybody? Circular. Okay, good. Let's see. Well, let's stay on that topic at 11. If we had a solution of methanol in water, would the deviation be ideal? I mean, would it be ideal? Would it be positive? Would it be negative? Under what conditions do you get negative deviation? Under conditions where the attraction between the solvent and the solute is higher than it would be for either pure solvent or pure solute. And in that case, we have a very strong attraction between water and methanol, which would impede the vaporization of either one and decrease the observed total pressure in the headspace. So I would expect a negative deviation for those two, which is C. I'm surprised at number 12, how number 12 affects students. I've asked this question before. So what are we dealing with in number 12? Osmotic pressure, right? So which way does water move across a semi-permeable membrane? Right? It moves from high water concentration to low water concentration, which is another way of saying water moves from low solute concentration to high solute concentration. So if we put a cucumber into a concentrated salt solution, which way is the water going to move? It moves out of the cucumber. Excuse me. It moves in. No, that's right. It moves out of the cucumber because the solute concentration outside the cucumber is much higher. So water is going to tend to move out of the cucumber. Right? And you're in the salt solution. Right? So the concentration of salt out here is higher is in here, and the water is going to move out to try to equilibrate. The osmotic pressure is applied from high water to low water. So the pressure drives water out into the solution. That's why A is the answer. And then the cucumber will shrivel up. What does osmotic pressure depend upon? Everything but what? Well, it does depend on molarity. Let's look at the formula. Okay. Molarity, ideal gas constant, and temperature. So the osmotic pressure depends upon molarity, right? It depends upon temperature. And the ratio of moles of solution volume is another way of saying molarity, right? So B and D are kissing cousins. The only thing that it doesn't say is that it depends upon atmospheric pressure. It does not depend upon atmospheric pressure. Now, the one caveat to that statement is it does not depend upon atmospheric pressure as long as the pressure so we have well, let's use the proper terminology. This is hypertonic, and this is, let's just say, water, or hypotonic. So water is going to tend to move in like that, pushing up. As long as the pressure here and the pressure here are exactly the same, it doesn't matter, right? But if for some reason you can isolate this one and apply pressure here, in excess of that, you can drive it backwards, right? So that question is a little tricky because it doesn't depend upon atmospheric pressure in the formula, but we can force it to go backwards if we apply a pressure that's greater than the osmotic pressure in that tube. That's where you get reverse osmosis. Okay? If you apply pressure in reverse, then you'll get water moving out. Right? And there are many places in the world now that use reverse osmosis to provide drinking water for their people where they don't have a lot of available fresh water. Okay. And we do it in the lab also. Right. We used to have a system in the lab where I worked, a reverse osmosis system for the whole building. Right. So it would provide, we'd pipe reverse osmosis water to every lab, but that's still not pure enough. So we take that feed and run it through a high purity system, and then that would produce pure water. Okay. We got about 15 minutes left. let's see. We're still in the easy section. Let's move into the moderate section. Let's see. Number one. The solution I gave in the handout is very technical. I wonder if we can deal with this one logically. Well, let's see, what formula is operative here? The molar mass of a solid as determined by freezing point depression. Okay, in order to do that, to use freezing point depression, we need to use this formula. The constant for freezing point, and then the molality. Actually, some of those questions imply a Van Hoff correction factor. All right, so we should include that in. Okay, the freezing point depression is 10% higher than the true molar mass. So what does this expression tell us relative to molar mass? Well, molar mass is determined by mass per moles. Okay? So if we've got an error of 10% here, it's not due to the mass. Well, it could be. But the question is, which of the following errors could not account for this discrepancy? The discrepancy could be accounted for by misweighing, right? So, well, some solid was left on the weighing paper, would decrease the mass, but it would also decrease the moles, right? So that's not a good answer either. If we rinse the solvent, but we don't dry it, then that means we decrease the concentration here artificially. If you decrease the concentration here, you're assuming that you've decreased the number of moles, which you haven't, because the value is higher. So E can't be it. Well, no, E could possibly, yeah. If you decrease the concentration here, the molality is moles per kilogram. So you're increasing this value artificially, which should also increase that value artificially. So no, this is decreased as a consequence. Because if you increase this, you still got the same number of moles, and you're artificially expressing those number of moles here, which decreasing this increases that value. Right, so E could possibly be it. We haven't looked at C yet. The solid dissociated slightly into two particles when it dissolved. If it dissociated into two particles, that means this is going to be greater than 1. And if that is increased, and this is constant, and that's constant, then this would have to decrease. Which would decrease this, which would decrease that, which would make this higher. But it would it be 10% higher? That's the question. You know, that's not a very good question. Let me check to be sure I don't have one like that in the exam, because that would not be fair. I may have already decided, having seen that one, have decided that it's not fair. Yeah. Okay, no worries. Don't bother with that one. Let's see. I only got 10 minutes left. Let's see if the difficult ones are worth investigating. Okay. We did this one. Something, number 4 was kind of like that one we did in the PowerPoints. Yeah, okay, so I won't need to do that one. How about, how about number 2? That actually has a practical application. A solution is prepared from 53.8 grams of non-volatile, non-dissociating solute and 85 grams of water. Then we're given vapor pressures. And what's the molar mass of the solute? All right. So what are we given? We're given 53.8 grams of the solute. 53.8 grams. Let's say the solute is X. And 85 grams of water. Okay. The vapor pressure of the solution at 60 degrees is 132. So the total vapor pressure, actually, let's just say solution. The solution vapor pressure is 132.4. at 60 degrees. Okay. The vapor pressure of water is 150 torr. So the vapor pressure of the solvent, which is water, we'll call that 0 because that's the solvent, is 150. So what do we need to calculate the molar mass? Is mass per mole. We got the mass already. We need the number of moles. So how can we use this information to give us moles? Well, it looks like we're dealing with Rayleigh law. So this is a non-volatile solid. We can use Rayleigh's law here. Mole fraction of, in this case, water, and pure pressure of water. Right? So we know what the final pressure is here, torr, and this is 150 torr. Right? So we can solve for X. The mole fraction of water equals 132 divided by 150, which is 0.88. Right? But we want to know something. We want to know about the moles of the solute. So the mole fraction of X is equal to 1 minus that, which would be that. Right? So that's the mole fraction of X in this solution. Right? So now I need some more space. Right? So if the mole fraction is 0.12, mole fraction of X is 0.12, what does that mean? Well, that's the moles of X divided by the moles of X plus the moles of water. Right. So, do we know the moles of water? Not yet. We can convert grams of water into moles. We just need 18.02 grams per mole. Right? 85 divided by 18.02 is 4.717. Right? So now, if 0.12 is equal to moles of X divided by moles of X plus 4.717, then we can solve. We've got an equation in one unknown, and we can solve for that. Which should be 6432. Moles of X is 0.6432. Now we've got mass divided by. The molecular weight then is 53.8 grams per 0.6432 moles. And that should be 83.6. So here's a case where we used a colligative property to find the true molar mass.
Notice you submitted a request in the past for some information regarding.
We determined the true molar mass here. And recall from first semester, when we had percent composition of a compound, we could do the empirical formula easily, but we couldn't go from empirical to molecular formula without the true molar mass, and this is one way to find it. This is the way you would find it for a non-volatile compound that's soluble in water. Okay, out of time. Is there anything we didn't cover that you need to cover, or any questions? So the exam 1 is next time we meet. It'll be due on what date is that? Here it is, on the 9th of June, which is next Tuesday. And we won't talk about the exam unless you have serious issues with any of the questions or problems like that. Otherwise, we'll go right into the next chapter, which will be 12. I think 12 is kinetics, isn't it? Okay. So the exam is timed, but when the time runs out, you don't get kicked out of it. All right. So don't be anxious about having enough time to do the exam. It's just a way of telling me whether you went over the 2 hours. 2 hours is enough. I mean, I wouldn't want to spend more than 2 hours on an exam if it was me. But if you need it, you can use it. And the exam is in Blackboard, like I showed you at the beginning. Okay. All right. So I'll post this video pretty quick. And we'll see you next Tuesday. Bye-bye.